Okay, hello again. So we're continuing with understanding Newton-Raphson in a new way and understanding its convergence rate. So the great new result we derived last time using Taylor series in particular, and Taylor series within sort of its Lagrange remainder form, which is very powerful, using a lot of proofs that use Taylor series. And now we want to get some condition on the gradient and its maybe second derivative that tells us when it will converge as well. So the second order tells it, given that it does converge, it will converge at this rate. But now we want to prove the theorem that we set up last time about the rate of convergence. Just before we get back into the final bit of maths, let's look at some pictures. Always useful, as I said, with this topic to look at it analytically in terms of diagrams, in terms of code, look at it at many different angles, and hopefully that can help. That's my advice, especially as it gets more complicated as we go on with this module. And here's an example of a convergent example of a Newton-Raphson. See root here, so the first value shoots from x0 to x1, the next value goes to x2, and you see it's nicely converging to the root, and that's what we expect most of the time. But here's an example when it doesn't converge. Now, last time I just drew schematically the worst example when you've got gradient at 0. Well, this is an example where you start at x0 at this point, it goes down to x1. Now it goes slightly to the left of the minimum, but still it's pathological because x2 turns out to be further away from the root than x1. So if we carry on this iteration, it will diverge. Okay, and there'll be other examples of this in the tutorial you do on root finding. It's sort of a really nasty example of it not working as we go forward. So that's our motivation. So you're looking for to prove this expression in terms of f double prime, and f prime. Let's move over to the board to continue our analysis. So last time we got to this point, we had we manipulated Newton-Raphson into a fixed point form. Remember, for fixed point we had this very useful result that G prime modulus has to be less than 1 for convergence. Well, we want to be able to use that by squeezing Newton-Raphson into that shape. And of course, it's not the same algorithm, but this is the way it goes. So what we did is we found that G psi of m equals psi of n minus f psi of n equals psi of n at the root. Okay. So now we have this G prime. This thing is our G prime, sorry. So we now need to differentiate this to use our result on G prime. So that's why we've manipulated it into our Newton-Raphson, fixed point form. Okay. So what we have here then, we're going to differentiate with respect to psi n. So that's easy. That's just like differentiating x with respect to x. And then we have our quotient, yeah? So this is just a quotient using our quotient rule. So we're going to use the quotient rule of calculus. Okay, and then we're gonna establish what G prime. So I just realized from the last when I looked at the last video that some of the edges of my text got missing, but I don't think it affected the meaning. If it did, email me and I can clarify anything. As I say, the lecture notes should be perfectly clear, but you know, and I don't think it affected the meaning, but I do check these things and try and do my best to give you as quality a video as possible. Yeah, and basically trying to imitate what it would be like to sit in a lecture theatre. Yeah. Which, believe it or not, when we do get that opportunity again, whenever that is, we're sort of going to run back to the lecture theatres, you know, maybe. So the differentiating psi n just gives us 1, and then we use our quotient rule, so we get v du by dx essentially. So that u is f of psi of n. Okay, so this is u and this is v in your quotient rule, minus u dv by dx, which is f double prime, okay, because we're differentiating f, all over v squared. Now remember, there was a squared of f prime in the thing we're trying to prove, so that's a good sign. We're getting closer to it. Okay, so we have a little bit complicated expression now. We have f prime psi of n minus f psi of n f double prime. But just have a look and see. So I'm going to pause for 10-20 seconds, as I would ask in a lecture theatre environment. Can you see any simplifications that jump out here? So that's right, those who saw it. This is f prime squared and this is f prime squared, so this term just becomes 1, yeah? This section of so this lot of the quotient equals 1. So that cancels with the 1, which is great. So we're just ending up then with an expression in as that we're kind of seeking, really. So that's the way the proof goes. So let's just finish this off. So g prime psi of n equals now f of psi of n, f double prime psi of n, f prime psi of n squared. Right. And we know from our fixed point theorem that g prime psi of n is less than 1 for convergence. So we've done this result near to the root. We've come up with something that looks like g prime, and we're using that. So now we can say that the modulus of this saying less than 1 for convergence. So that's proving our theorem. Okay. Okay, so all we've done is we've so in just to recap verbally, I might just go back to my face. That's really with all the data scrawled all over it. Just to recap, so this is the most complicated derivation really in terms of convergence in the root finding section of this module. We've established two things. We've established quadratic convergence of the Newton-Raphson method, which is involved using Taylor series, and getting an error law that goes to e to the n squared. And then we've also established condition on the gradient for convergence, and we've manipulated it in terms of the proof of that, and manipulated it into terms of fixed point method, and then using g prime is less than 1 result. So put together, you can then now actually quantify with your derivatives at any point whether this method's going to converge if it's near the root, you know. So this one that's diverging is going to have f prime very small at this point, so that that product is going to just go greater than 1, and or so that's going to be violated. Okay, so I hope to see what we've been doing in this first week and a half of this module is that we're revisiting old friends in terms of numerical methods, and then trying to analyze them a bit more rigorously, understand what, you know, their different convergence rates. So now, when your Newton-Raphson method is faster than your bisection method for a certain function, as in we'll look at in the practicals, you can say, because it's second order. And the ability to say that and to know where the proof is where the mathematician earns their money, if you like, in all numerical methods, wherever you find them out in the world, and, you know, in the examples I gave right in the introduction. Okay, so I normally try and do the videos at 20 minutes, but this is a very convenient place to stop. The next topic is the last topic in just bending down to my notes here. In root finding, which is we've done all our methods so far are in one dimension. So, but these methods really come into their own if you look into multiple dimensions. So what we're going to do is look at Newton-Raphson method in 2 dimensions, but given that's a sort of a bit more a self-contained topic, I think I'm going to wait to the next video. So see you then. Bye for now.